and Tauberian theory.
Uh, Thank you very much for giving me the opportunity to speak here. It has been a wonderful conference, and I'm equally excited about the fact that this is the first time I'm in the south of the equator, so that's exciting. And today I'm going to talk about Litecoin modular bootstrap and is the connection with Tauberian theory and how we can use the Tauberian theory to say something universal about some set of 2D CFTs. So this is a work, this talk will mostly be based on this work we put out recently with Jaishin Chow. And a lot of the estimates, and we heavily use the framework from an earlier paper we wrote with Slava and Jaishin back in December. So today the main goal or the main premise of the talk would be to understand the irrational 2D CFTs with Virasoro symmetry only. So the thing what do I mean by irrational? So basically I mean that these are, of course, modular invariant, unitary CFTs. Then the central charge is greater than 1, which basically means there are infinite number of Virasoro primaries. And then we also need to impose this condition that we are only looking at CFTs which only has Virasoro symmetry. So we basically impose a twist gap condition. So.
Sindri, do you mind to write a bit bigger? The writing, if can be a bit.
Oh, sure. Okay. Okay. So the twist gap is greater than 0. So I'll use this notation that tau gap is twice times t. And also I will use the notation for later part. A is c minus 1 over 24. So A is strictly greater than 0. So with these conditions in mind, we want to understand the universal features of these CFTs. In particular, we want to know some Cardy-like formula for large spin and small twist. Also, this has been argued previously that for this set of CFTs which are modular invariant, unitary, and has a twist gap c greater than 1, there is a twist that the twist gap has to be upper bounded by, so tau gap has to be upper bounded by c minus 1 over 12. And not only that, this c minus 1 over 12 is an accumulation point in twist. Accumulation point. So these have been argued previously by various authors, and we established this as a theorem in this paper, which basically gives us a rigorous framework. And staying within this rigorous frameworks, we can ask more detailed questions about this regime where the spin is very large, and that by small twist I mean the twist around this point c minus 1 over 24. Yeah. So one assumption is you can assume the CFT is compact, so the spectrum is discrete. If you do not assume the spectrum is discrete, you have to assume that there is an identity. So the statements I'm going to make that will also be valid for CFTs which has an identity and a continuous spectra, or you can relax that to have a discrete spectra also.
If you only look at partition function, then I would assume that just assuming having identity is not enough, because you can always imagine that there's a very large density of primaries above some gap that overwhelms. It's not obviously because I can imagine a limit, where the spectrum looks like that of a non-compact CFT with a gap, just because the partition function is dominated by a very large density of primaries above some gap.
Wait, how? So the statement is, as long as the modular invariance that directly tells you that if you have an identity, then and there is a twist gap, then this has to happen, and there is accumulation point in twist. There's no way out, no way out from this.
No, I understand, but of course on the other hand, we also know irrational CFT without identity that saturate this gap. So I'm just saying.
Oh, are you asking whether this condition is like a sufficient or something like that? Sorry, I mean necessary?
No, I guess I'm trying to say that it may not be possible to improve this constraint. I mean, after all, certainly we don't have any example that close to this among compact CFTs, and there are, of course, examples for non-compact CFT that saturate this gap. So if you want to go anything beyond I'm not sure just assuming having the identity operator is enough.
Well, this is a theorem. We proved it because.
No, I understand. You can prove the theorem, but I'm saying that I'm saying that this result is not very strong. Because we do not know any example of the twist gap that's non-zero for the compact CFT, and in fact, it's not even clear if they exist to begin with.
Yeah, I agree. I mean, we do not know any example of this kind of CFTs. That's true. But then, if you assume this set of things, then some statement follows. And if someone comes and gives me a concrete proof that this CFT cannot exist, I will also be happy. Right? Yeah.
So you are excluding the identity, or this is above the identity?
Oh, this is above the identity. Yeah. Identity is there, and then there is a gap. Yeah. Okay, good. So the question we are going to ask is, as I wrote here, we want to understand the density of primaries, density of Virasoro primaries around twist C minus 1 over 12 and large spin where j goes to infinity. And as we all know that in a compact unitary CFT, the spectrum is discrete, so the density of states is really a distribution. So a proper way to interpret this formula is to smear it out over some window. So the next question we're going to ask that whether there is a universal size of the averaging window. So these two will be the main questions we are going to ask. And of course, people have argued like some formulas for density of Virasoro primaries based on intuitive arguments and using light cone bootstrap. And those rough arguments goes like, basically you look at the partition function with some different left moving and the right moving temperature, and then you take beta L to infinity and beta R to 0. And you also make sure that beta R inverse is much, much larger than beta L. And once you assume this, you can show that in the dual channel, this is basically dominated by the vacuum. And then the naive argument goes like, you take the vacuum, you basically do an inverse Laplace, and that gives you a density of Virasoro primaries. And of course, in this perspective, when you say that in the dual channel, this thing is dominated by the vacuum, you can make it more precise, which has been done in this paper. So some of our estimates I will show that will involving a more precise version of this limit. Okay, is there any question at this point? Good. Okay. So let me first briefly review that, like how this kind of problem is set up and how we can access the averaging window by smearing the density of states in a very general framework. So let me review the usual Cardy formula. So the way usual Cardy formula works, we want to figure out the density of states for large delta. So we want to figure out the behavior of this density of states as large delta. And the idea is that this thing is encoded in the partition function in the beta going to 0 limit. And we do a S transformation using modular transformation. We basically write it as this. And this thing has a universal expression, which is 4 pi square over beta, c over 12. And then we take this quantity and do an inverse Laplace. And this naive inverse Laplace transformation gives us some number times delta minus 3/4 twice c delta over 3. So this is the naive Cardy formula. And the more precise version of the Cardy formula is basically some smeared version of this, where we can show that this rho of delta prime, d delta prime, if we smear over some small window, which is of the size of delta, where delta is some order 1 number, and if we take delta going to capital delta going to infinity, this quantity has an upper bound and a lower bound, which goes like this. Where this function rho 0 delta is precisely the Cardy formula, and there is some prefactor which basically tells you like how you are averaging over this window. And so our goal would be to write down some inequality of this form, where instead of looking at the large delta, we will be focusing on this regime where the twist is around c minus 1 over 12 and spin is very large. So our aim is to write down some inequality of this form. Okay. So the first question is that how do you incorporate, how do you set up a problem so that we can derive this kind of inequality and refine the naive version of this density of states. And to gain some intuition about how this works out, we should first look back at rho of delta as some inverse Laplace transform of partition function. But of course, this, like as such, this equality doesn't make any sense because we know that this is a distribution. So at some point it goes to infinity, some point it is 0. So this integral is not well defined at all. So this integral is not well defined. And to make sense of this integral, we should cut off this minus infinity and plus infinity at some finite point. So our next attempt would be to understand this integral, where the integral goes from minus lambda to plus lambda. We have the partition function. And we introduce some function which has a compact support which cuts off the integral from minus infinity to plus infinity to this finite interval minus lambda to plus lambda. So the first point is this integral is well defined. We can hope to estimate this integral and do something about it. But now the point is, because I have stuck in this function, like I do not know what this means in terms of this delta variable. So that means I cannot just put in any compactly supported function. I need to have some control. And to see how we can control this function, we should go back to the delta variable. So basically we introduce phi of delta prime, which is phi hat plus minus t per I delta t dt. So basically from this domain, I go to delta prime domain. And if you plug this in and do the t integral, then you will see that this becomes minus infinity to plus infinity rho of delta prime phi plus minus of delta prime e power eta delta prime to prime. So here I just written down the partition function as an integral over the density of states, and basically I did the t integral. Once you do the t integral, the delta integral remains, delta prime integral remains, and it looks like this. Yes. Sorry, I should write like this. Yeah. And yeah, at this point there is no small delta, but you will immediately see how the small delta comes about. But originally we wanted to estimate this integral over here, and this integral is rho delta prime, some the characteristic function of delta prime, where this characteristic function has support only on this interval, which is centered at delta, and like this. So we want to estimate the integral of rho delta prime with the characteristic functions which are support on this, and on this side I have rho delta with phi plus minus. So basically what we want this phi plus minus to approximate these characteristic functions from above and below. So let me use a different color. So we start with this, and my phi plus would be some function which goes like this. So this is phi plus, and phi minus would be some function which approximates this thing from below. And then there is a condition that this phi plus and phi minus are band limited functions, which basically means in the Fourier domain the support is compact, which is from minus lambda to plus lambda. So and from the math literature we know this kind of function exists given a lambda. So we use these functions, and using these functions we can immediately write down an inequality which is of this form, that rho of delta prime d delta prime is upper bounded by speaking plus IT phi plus hat t dt. And on this side, this looks like minus delta, and you have the same integral, but instead of phi plus, you convolve with phi hat minus t dt. And as I was saying, that these integrals are well defined on both sides. Yes.
Shouldn't it be b times small delta, based on what you wrote there, b delta minus delta prime? You had an exponential e beta delta.
Yeah,
minus
but then I guess, yeah, I jumped some steps, but then so you write this as, so this is same as this.
Okay.
And yeah, there should be a IT delta, you're right. Yes. Yeah. Yeah, but so what you can do, you can also redefine your phi hat minus t so that it gets absorbed, so that it basically this is centered at delta rather than 0. Yeah, so it's yeah. I was a bit sloppy.
Sorry, I got a bit lost there.
Yeah,
so
sure.
you just define this cutoff integral, but there's no left-hand side, so we don't know what this is equal to.
Yeah, we do not know.
So where is the bound coming from? Sorry.
Oh, because this phi plus and phi minus approximates this function here. So I jump some step. So this thing. So okay, let me write it down. So from this thing, you can write this inequality, rho of delta prime, phi minus delta prime, e power minus beta delta prime, this stuff here, and the same stuff with delta plus delta. And then you go to the t variable. That gives you the inequality here. Okay, good. And I must say that this technique of like proving bounds using this way is very general and appears in many places in math. So now once we have these things, our job is to estimate this integral. And the way we estimate these integrals, we basically go to the dual channel. So we write it down as z of 4 pi square over beta plus it. And then we separate it out in two pieces. One is the light piece, which basically is the vacuum contribution and all the contributions from states below C over 12. And there is a tail contribution, which is basically contribution from infinite number of states above C over 12. And then roughly speaking, the idea is that this light part will give you the Cardy formula with some extra factor. And the heavy part will control the size of the window. Because you want the heavy part to be suppressed compared to the light part, because the light part gives you the leading thing. And the condition that the heavy part is suppressed compared to the light part will give a constraint on this lambda. And this constraint on lambda will put a constraint on delta. And that's how, so one of the main messages that comes out of this analysis is that the size of the averaging window is controlled by the heavy part and controlled by the tail of the sum. Whereas the leading part comes from the vacuum in the dual channel. So so this is the basic framework, and we are gonna use this framework in the case of the light cone bootstrap. In particular, in the case where we want to estimate the density of Virasoro primaries around this point. Is it clear? Yes. This C minus 1 over 12? Oh. Yeah, that's a good question. So if you look at this function, the real part of the function, this function has a different behavior as a function of t when you below C over 12 or above C over 12, because the factor goes like delta minus C over 12. So basically when you estimate, you need to estimate the two things separately. That's how this C over 12 comes from. Yeah. Okay, good. So this is the framework we are going to use. And okay, I'm running slow. So at this point, I have two choices. Like first, write down the theorem we prove and just go on proving the theorem, but which would boil down to writing tons of inequalities, which I am not going through now because it might look scary. So what I'm going to do, I'm going to present our results, what we can achieve by using this formalism and some of the frameworks we developed in the earlier paper. And once we present our results, I will state the theorem, and then depending on the time, I will sketch the proof of the theorem or go into details and so on. Okay. Ouch. Okay, for the statement of the theorem, so as I was saying, that we want to estimate the number of operators in J inside some interval, which is A minus epsilon, A plus epsilon, where you have H plus J. So we want to estimate the number of operators inside this window as J goes to infinity, and I will say what the, and also we want to mention that epsilon is a very narrow window, so epsilon is kappa J to the power minus half log J. So as J goes to infinity, epsilon goes to 0. So this is a shrinking window. So pictorially, I am trying to estimate this thing where you have H and H bar, and these are the fixed spin lines. And say this is your point A. So basically, we are trying to estimate the number of operators inside some narrow window as J goes to infinity. And the size of the window becomes smaller and smaller, like J to the power minus half log J, with some value of kappa. And kappa also has a constraint. So kappa has to be in this interval for A 3 over 2 pi times t, comma infinity. And one important point is that kappa is inversely proportional to twist gap, so which makes sense because this analysis is contingent upon the fact that there is a twist gap. If I make the twist gap vanish, then the result falls apart. So here it's important that kappa is 1 over t. So once we have this setup, we can actually estimate the number of operators in this narrow window, and the result looks like following. Which is in J, epsilon is J to the power minus 5 quarter e power 4 pi A square root A times J plus some correction, which is basically like logarithmic. So we can bound this thing of J, which is 3 log J plus 1 plus some finite constant, which doesn't matter. So the important point here is that in earlier, whenever we derived some precise form of Cardy formula for large delta or fixed spin large delta, most of the time we are restricted to the scenario where delta is some order 1 number. For example, in this, if you look at this inequality and if you look at the lower bound, you will see that if delta is less than half, then the lower bound is kind of meaningless because it's a negative number, so it doesn't say anything much. Whereas here, we have been able to show that the Cardy formula is actually valid in this regime, not only for an order 1 window around this interval, rather a very narrow window which goes to 0 as J to the power minus half log J. So that's one significant improvement over the previous results, and is only possible because there is a twist gap. Yeah. Yes.
I'm a bit uncomfortable with the logical possibility that there's no theory where your theorem can be applied to. Does your result, is there some way to, does your result give any hint on, if one tries to look for, compact irrational CFTs with a twist gap, how would you use that to search for such a theory?
Yeah, I don't have a very smart answer to give in terms of how do you search for it. For example, Connor and Antonios are looking for irrational CFTs by deforming this coupled stuff, coupled minimal models. But I'm not entirely sure whether they can access this regime in the perturbation theory. Probably not. So.
But I'm just saying that even with such a prediction about the spectrum, I mean, if you can you apply this in a converse direction? I mean, if you have a theory that has this kind of density of states, it's not like you can say for sure.
So you can do one thing. So there is another possibility. There is another possibility that so all the techniques we develop, you can assume that you can modify, you can relax the condition of twist gap a little bit. You can assume that how many currents are there and so on. And if you input that information, you can modify the whole analysis a little bit, and then you can have some prediction. So in that sense, the technique has some predictive power for other scenarios where you have some currents. This is the simplest scenario where the theorem and everything is clean, where you have a twist gap. But I don't think just from this analysis we can say anything about how to construct the irrational CFTs. Like, I think it's a very hard problem. Yeah.
Sorry, your kappa depends on the twist cap T.
Yeah.
Are you agnostic if that twist cap comes from a single operator of twist T or an infinite series of operators who accumulate to T?
Okay, yeah, that's a good question. Again, so the point is, if you insert finite number of operators below this gap, so what I'm saying that suppose you allow for 0, h bar or h, 0 operators, but finite number of them, then nothing changes. It's the same result holds, because the asymptotic doesn't really care about whether there are a finite number of them.
What if you have an infinite series that accumulates to T? Would this result also apply?
Oh, infinite series accumulates to T.
Yeah.
Like you mean from below?
No, I mean, I think...
From above, I think it's still fine.
Okay.
From below, there might be subtlety, yeah.
Okay, thanks.
Oh, yeah, that's also true, yeah, that's true. You can just decrease the T a little bit, yeah.
What happens to the window for large C, since kappa depends on C?
Yes, wait for 5 minutes. I'm going to write down a result for large central charge, yes. Okay, so where was I? Yeah. Oh, so another important point I want to emphasize here, that when you do a naive analysis of this kind of, take the dual vacuum and do an inverse Laplace, the support of this inverse Laplace is always above this line. But if you do it rigorously like we did, we cannot really rule out a possibility of having something below the threshold. So that's an important point I want to emphasize. And from our analysis, it looks like there is no way to rule out this possibility unless we put in this by an extra assumption that some states leaves below C minus 1 over 12. And if you indeed assume that there are no states below C minus 1 over 12 or below this A, then you can predict a cleaner lower bound on this number of operators where you have perfect. So here you can see that the power index of J has some uncertainty because of this term. But if you assume that there are no states for J greater than J star and H less than C minus 1 over 24, except for the vacuum in this window, then basically you can prove a lower bound where the power index is fixed. So this is some positive constant, J to the power minus 5 quarter, and e power 4 pi aj. And another important point is that one can always do the naive Cardy analysis, and this will give you a continuous function. And so you can take that naive answer and try to estimate what are the number of operators in this window. So the naive answer will predict we'll predict in this window the number of operators is epsilon to the power 3 over 2, j to the power minus half, e power 4 pi square root aj. And you can see if you plug in epsilon equals j to the power minus half log j, you will recover this 5/4 minus 5/4. So the naive analysis in the leading order gives you the right answer. Yeah, for yeah, the naive analysis with wrong epsilon, yeah, you might get rubbish. Yeah, I agree. At least there is no proof that it holds, for example, epsilon much smaller than this window. Yeah. And another point to make that, which is kind of obvious at this point, that earlier the result was that there is a twist accumulation point around c minus 1 over 12. So around c minus 1 over 12 you would find operators, but now we have a much more specific information. So in that sense we can say that the accumulation happens like this. So we can basically say that for every spin how this accumulation happens. So that's, in some sense, that's a refinement of the twist accumulation result, but which is kind of obvious from the statement that we have an explicit form of how many operators are there. Okay, so this goes for, so this is for the fixed central charge CFTs. And now we can also look at CFTs which are holographic. So basically, which means that we are looking at a family of CFTs where central charge goes to infinity. And this comes back to Nima's question. And then we will have some sort of results for this kind of quantities. And let me write it down here. So it turns out that to prove a similar statement for the holographic CFTs where central charge goes to infinity, we need to assume something more, which is basically you can think of some sort of sparseness condition and things like that. And roughly speaking, this comes about because when you have at a fixed central charge, the partition function for finite beta is finite. But when you take the central charge going to infinity limit, the partition function at finite beta may not be finite because you are taking one parameter to infinity. So these two conditions basically tells us, so this basically forces us to assume something more. So the first assumptions we will make is that the twist gap is linearly growing with C. So as A goes to infinity, we are looking at a family of CFTs which satisfies this condition where alpha is independent of A. So this is in some sense the sparseness condition. And we also need to assume a more technical assumption which might be derivable from some weaker assumption, but we haven't tried hard, which basically says that the partition function, in particular the partition function for the Virasoro primaries, not the full partition function. If we just consider the vacuum contribution, then this ratio is bounded by some number which only depends on beta L and beta R if beta L and beta R both are greater than twice pi. So if you assume these two conditions, you can think of them as a proxy for the sparseness condition. Then we can derive some result involving the density of Virasoro primaries around this twist. And the result goes like this. So in this case, A goes to infinity, which basically means the central charge goes to infinity. And the spin goes to infinity in the following way. So the spin has to grow faster than C cube. And one intuition for this is that, like the way the saddles are related, the beta R, so roughly speaking, that when you go from the canonical ensemble to microcanonical ensemble, beta R is related to j in this manner. And if you want to do light cone bootstrap, you need to let beta r to 0, which basically forces you to choose this limit. So under these conditions, in this limit, we can show that in j, and now we can allow for epsilon 1 and epsilon 2 because they scale differently with respect to a and j, which I will write down soon. This goes like, again, there is a Cardi-like growth. And then there is a correction which goes like this. And this epsilon 1 and epsilon 2 again depends on the twist gap. And so this is 1 over pi alpha, where alpha is this parameter. So again, it's important that alpha is non-zero. J log aj. And epsilon 2 is basically 3 over kappa, some number, square root a over j twice pi a log j. So that's the version of this formula in the large central charge limit. And holographically, this basically means that you are looking at near extremal black holes, which are highly rotating because spin is very large. And some of these limits are actually intuitively understood in a paper by Ghosh, Maxfield, and Turiachi, where they show that in some limit which is kind of similar to this, there is a vacuum dominance in the dual channel, which is related to the BTZ black hole dominance, which is rotating. And there is a Schwarzian sector which basically controls the left moving part. So in the right moving part, there is a BTZ black hole dominance, and in the left moving part, there is a Schwarzian sector. Our regime is slightly different from them because, so in their regime, the j over a cube is some order 1 number. And we have tried to make their analysis rigorous, but we failed. So what we could do that if we take this limit, we can show that there is a dominance of BTZ black hole in the canonical ensemble. And if you translate that statement to the microcanonical ensemble, you will see that the states that dominate are basically in some narrow window around c minus 1 over 24. And if you just care about the dominance of the BTZ black hole in the canonical ensemble, then we can prove their results. But the point is that when you say that something dominates, you want to be able to say it both in the canonical ensemble and the microcanonical ensemble. And yeah.
Hi, can I ask a question just to make sure I understand?
Yeah.
Is a corollary of your theorem the following? Suppose you have an irrational CFT with only Virasoro symmetry, then does your theorem seems to apply that the spacing of energy eigenvalues, like if we forget the spin, the spacing of nearest energy eigenvalues at large energy has to go to 0. Is that right?
Large energy fixed spin?
No, forget spin. But it implies that for 2D CFTs, 2D irrational CFT with finite twist cap, if you go to next to nearest deltas, that goes to 0, which in particular is not true for rational CFTs.
Wait, sorry, in this regime or in this regime?
In this regime. No, in this regime. So forget spin, just grade by delta, forget spin. So sum over all the different, and then if you organize the states by delta, it seems to imply that the next to nearest energy eigenvalues, the spacing has to go as like delta to the.
Oh, you are for yeah. I think yes, that's true because the twist has accumulation point.
Right.
So basically, you are saying that I point the dots and project everything onto one axis. That's what you are saying.
But to the delta axis, not to the h axis.
Yeah, but if I think that would also be an accumulation point. Yes.
And probably you thought about this, but is there any hope of like if you optimize an epsilon, instead of making it j to the minus 1/2, something exponentially small in square root of j or something?
It looks extremely hard from our analysis. So from our analysis, it seems that this is like near, at least this number might not be optimal, but this behavior looks like optimal because there is no way to squeeze it, make it like exponentially small, but.
Yeah, but I'm just saying sum over the different j's with the same delta. Then the deltas goes to 0. It's not true for rational CFTs, for example.
I think he is talking about forgetting about j, I think, yeah.
We can discuss that.
Okay. And is there a question? Okay, so there is one more point I want to make, that so there has been papers, there are papers back in 1991 around that time by Preskill and other people where they showed that the black hole thermodynamics breaks down in the near extremal limit. So in this recent paper by Ghosh, Maxwell and Turiachi, they argued that this is not the case, because if you are very careful enough about this near extremal limit, then you can show that the BTZ black hole dominates and there is some sort of equivalence between the microcanonical and canonical. So you can interpret our results as some rigorous and refined version of their statement. So basically what we are saying, that the black hole thermodynamics works as long as the spin and the temperature like satisfy this inequality. So this is the black hole temperature, this is the black hole spin. So you can think of the statement by Preskill and other people as they were saying the temperature has to be very larger than 1 over c for the black hole thermodynamics to hold. But here we basically say that there is a ensemble equivalence even in this regime, as long as you are looking at very highly spinning black hole where j over c cube goes to infinity, and the temperature is in this regime, the black hole thermodynamics works, means that there is an equivalence between the microcanonical, canonical, and the grand canonical ensemble. So that's one of the outcome for our result. Okay.
Sridip, can I, sorry to interrupt you again, but coming back to this comment by Nathan and so on. So this is an important point that I'm missing as well. So this nj of epsilon, so you prove that there is at least as many primaries in this window.
Yeah.
But what do you actually know, like could these primaries can they be actually exactly degenerate in delta?
Yeah, they degenerate in delta.
Yeah. Well,
so for example, if you are in this window, then it can happen that all the operators are, say, in the endpoint. That can happen.
But if so, then you cannot show what Nathan asked you to show. Because if they're all degenerate in delta, then okay, then they're all degenerate in delta.
I thought what Nathan wanted to say, that maybe I misunderstood. He wanted to say that I forget about the spin and I plot all these operators here and project onto this axis.
No, he wanted to project on the delta axis. He wanted... Yeah.
Ah, I see. Okay, sorry, I misunderstood. Okay. Yeah, definitely, because we cannot really tell like exactly where these operators lie. So yeah, so there can be options of but then you can probably show that it cannot be completely degenerate. For example, you cannot just take all these operators and put it exactly at one point.
That's the question. So you can...
How would you prove that from this?
So that's some other result that you feel you could show, but it doesn't follow.
Yeah, I think it doesn't follow from here. So probably what you can try to do, which, well, I'm not entirely confident. So which you can try to do, you can try to put all the operators on one point and follow that trajectory and try to show that that is inconsistent with the, for example, okay, I can probably show that if all these operators lie on this line, then that will be inconsistent with the...
Make it move. Inside this tiny box, you could make it
Yeah, you can make it move, yeah. Yeah, I agree, yeah, you can make it move, yes. So, of course, there can be scenarios that where things lie on the line, yes.
Okay.
Yeah. I think it's, so the point is the accumulation point happens in the twist. So only in the twist variable there is a denseness. Okay. Okay, so this concludes our results. So now, in the rest of the time, I'm gonna tell you state you the main theorem we prove, and basically as a corollary of those two main theorem, this result follows. Okay. Yes.
Sorry, I missed. So what is the gravitational interpretation of these states with J over A cube?
These things, the statements would be, these would be like nearly extremal black holes with highly spinning. Yeah. And earlier there was some confusion about whether these are like whether thermodynamics holds for them. So there is this paper by Preskill and other people where, like, if you translate in the CFT language, that basically means the temperature has to be much larger than 1 over C. And then there is this another paper by Ghosh, Maxfield, and Turiachi where they claim that this is not the case. You can make it smaller as long as you take care of all the contributions and everything on the CFT side. And our version is the more precise and the rigorous version of this statement, that you can make the temperature much smaller than 1 over C as long as it satisfies also this bound. Yeah. Okay. Let me erase this part. Okay, the statement we are going to prove is about a quantity, which let me write it down. Before I mention about the theorem, so as I said, the idea is idea to derive this kind of results is to look at the partition function in the light cone limit. So we have to define a proper light cone limit, which is basically the following, where beta L goes to infinity, beta R goes to 0, and then we also introduce a parameter which is W, which is 4 pi square T over A, beta R goes to infinity, and beta L inverse log beta R goes to 0. And as I was saying that this beta R goes to 0, so it's like a statement in the canonical ensemble. If you go to microcanonical ensemble, so this beta R would be related to the spin. So we can also identify beta R or declare it to be the definition as this. And then this limit, the double light cone limit, is defined as beta L goes to infinity, J goes to infinity, and you have 1 minus W square twice pi T over A square root J over A minus beta L goes to infinity, and you have beta L inverse log J goes to 0. So in this limit, we will be estimate a different quantity which is related to Nj but not quite Nj. So we will define this quantity Aj beta L epsilon to be in H plus J power minus beta L H minus A. So clearly you can see that once we have some control over this quantity, we can put a bound on this quantity because you can write down a trivial inequality which goes like epsilon L Aj J is e power epsilon beta L Aj. So our idea would be to like put a lower bound and upper bound on this quantity Aj in this double light cone limit and then translate it back to some estimates about the Nj. So the theorem we prove, the statement is following. Okay, bear with me because it might look a bit scary, but so we pick the parameter in the range half comma 1, and once we pick this, we fix this, and then we pick the parameter epsilon. We should not say pick, like this epsilon should be in the range, which is 1 minus 1 over 2w, and from below it should be some epsilon mean, which can depend on j and a, and this thing is given by maximum of a 3/2 by square t log j over square root j and 3 log j over 4 beta L plus 2 log beta L over beta L. So the epsilon is in this range, and then we can show that Aj beta L epsilon divided by pi this thing has a lower bound and upper bound, which is given by a number which is 1 over w, 1 plus sinc twice by w epsilon, and the lower bound is 1 over w, or 1 minus c by w, 1 minus epsilon, where by this symbol I mean that limit a over b is less than equals 1. And so the idea is that as j goes to infinity and epsilon is within the range, and note that the minimum value of epsilon is log j over square root j, so this goes to 0. Here also log beta L over beta L goes to 0, and this goes to 0 because of the condition, this condition beta L inverse log j goes to 0. So basically this shows that I can make my window shrinking to 0, and even then that this quantity Aj beta L epsilon divided by this exponential growth is bounded by some number. And to derive the expression for Nj, which I erased the expression for Nj. So to derive the expression for Nj, you have to appropriately choose beta L and epsilon so that all these conditions are satisfied. So to derive the formula for Nj, so you choose beta L as 3 kappa inverse j to the power half, and epsilon to be kappa j minus half log j. And to satisfy all these DLC conditions and this condition, you have to also make sure that kappa inverse is less than some number, which basically relates to some statement about what the order 1 number in the actual window was. Okay, is it clear? And once we have this estimate, we can also do a similar kind of estimate for the large central charge regime, where basically like you have to define properly what we mean by the double light cone limit. For example, you have to make sure that j over c cube goes to infinity and so on. Once you have properly defined these things, then you can basically reuse the arguments that you used here with some technical caveats which you can tackle. And again, you can derive some result of this form, where you have some growth here in between and is upper and lower bounded by some number. Okay, how much time do I have? I think it's 15 minutes. 0. Okay, is it? Okay. The main statement I want to make at this point, so the way the proof works, so basically we want to estimate the density of states in this interval, and let me write it down one equality. So the idea is to estimate some, so basically you can rewrite this density of states as some partition function which only gets contribution from this a minus epsilon, a plus epsilon, and then you have these band limited functions phi hat t dt. And then the idea is that you show that this is the dominant contribution in the direct channel, and in the dual channel you show the dominant contribution comes from the vacuum. So if I write it down as I a minus epsilon, a plus epsilon, then basically the statement about the modular invariance is I0 plus I h t a minus epsilon I h in this range plus epsilon plus I h greater than a plus epsilon is the dual channel vacuum contribution plus the non-vacuum contribution. And what you want to show that you basically divide the whole thing by the I dual vacuum and then show that all the contributions are suppressed. Sorry, not this one. This one are suppressed and also this one is suppressed. And then you can separately estimate this vacuum contribution, which basically gives you the Cardy formula. And once you have that, you basically have your theorem. So, yeah. So that's what I wanted to say. Thanks.
We have time for some questions.
Question is about your sparseness condition. How robust, like, I mean, theories like this probably don't exist in holography or in any, like, if I was to add like a light scaler or something, would everything break or?
No, so you can always add finite number of things, nothing will break.
And you can carry, and
just
get modified in a small
yes,
way.
any finite number of things, nothing will break down. It's allowed.
Sorry, finite number of things with twist small?
Yeah.
But presumably if you add a light scalar with twist below like C over 32, there'll be an infinite Regge trajectory. So there'll be infinitely many operators of, but.
Wait, how does that says anything about, like, sorry, I didn't get
I'm
it.
saying if you have a light operator with twist, let's say order 1, then there'll be infinitely many operators whose spin goes to infinity, but their twist accumulates to some finite number, right?
Yeah, but how does that contradict anything?
No, it's not contradicting. I'm just asking, can you say something about those theories?
Oh, I see. So you are asking about this BMFT story.
For example, yeah.
Yeah, no, we do not have anything concrete or rigorous to say about VMFT.
Okay.
But presumably one can try to do something. And so the analog of the VMFT is the MFT story, where basically we proved some results, some rigorous version of the results. So it would be nice to prove some rigorous version of the result. We'll take the 4-point correlator and do the Virasoro blocks. But here, for example, so one thing that happens here, because we are dealing with the characters, which are basically these nice functions, which can do a lot of stuff. So things becomes much harder when you're dealing with Virasoro blocks, and even in higher D, like doing something similar in the higher D CFT would also be a bit trickier, I think, because you have to deal with hypergeometric functions and so on. But yeah.
Would you probe in principle the same information if you looked at the 4-point function on the sphere and did Light-Cone Bootstrap there, or is it very...
That would be the density of states weighted by the OP coefficients. Some statement along that line. So instead of integrating rho delta, you would be integrating rho delta C square delta prime over some interval. So Slava and Jaishin had some papers on 1D CFT using like a Tauberian things, like some precise statement. But that statement is for a region from 0 to delta rather than some order 1 interval. I think it would be also nice to promote that thing to an order 1 interval and then try to incorporate these things. So I think there's stuff to do in the higher DCFTs. Not much has been done. Yeah.
Thanks.
Hey, just a simple question. For this inequality with the temperature of the black hole to exist, also alpha has to be greater than C cube over J.
Alpha is the
Alpha
order
square.
1 number here.
Right.
So alpha doesn't play any role. So I mean alpha, so yeah, alpha is order 1, so it's always less than C cube.
Yeah, I see.
Yeah.
Any other questions? If not, let's thank Cyril.
Thank you.